My name is Omar El-Kasabi. I'm the team lead for the solar cells project here at Husky Satellite Lab. We are a research and development laboratory dedicated to furthering the capabilities of CubeSat technology, driven by students here at the University of Washington. Our team's focus is on designing a solar sails propulsion system that is capable of providing interplanetary travel for CubeSats. We have designed a system that is capable of transporting a 6U CubeSat to Mars within 2 to 3 years.
Solar sails operate on the principle of solar radiation pressure. High-energy particles from the sun strike the sail, causing a forward thrust. This thrust is dependent on the solar sail size and the material, so these are important parameters that we have considered when developing our system.
Since the system relies solely on solar pressure to provide thrust, we're able to accomplish this mission without needing a gram of propellant. We believe that this system is valuable to NASA because of their interest in furthering Mars's economy and our ability to provide reliable, continuous technology and infrastructure to Mars through our propulsion system.
Through the use of CubeSats, space exploration beyond cislunar reach is made possible at a lower cost, with better scalability, and a quicker production rate.
Because the mission uses no propellant, the traditional equations for thrust and delta V are no longer applicable. This means in order to find a sail area capable to deliver the designed mass of the spacecraft, about 15 kilograms, in the time of the mission, 3 years, we had to be creative and derive non-impulsive equations of thrust to fit our mission parameters. Based on this math and specifically chosen materials, we can send small spacecraft beyond the cislunar reach with a 60-meter squared sail.
Our solar sail system is hoping to employ a mechanized boom system.
So the boom design is a composite collapsible tubular mast.
The collapsible tubular mast, or CTM booms, are a promising candidate for the deployable structure by being stored on a CubeSat for many interplanetary missions. This is due to the omega-shaped shells that form a closed section to yield large stiffness and high dimensional stability. Due to the volume constraint in our CubeSat, having our height range of 60 to 70 millimeters tall will be a good range because it will likely be effective at accounting for viscoelastic creep and stress relaxations, as it exceeds the threshold by NASA's 6U CubeSat missions. We have two possible cross-section designs of having a symmetric or asymmetric booms. The symmetric cross-sections have identical outer and inner shells to make the manufacturing process simple and provide a higher area moment of inertia to give its high stiffness, and is designed to easily predict the loadings in multiple directions, but they have a lower bistability. For the asymmetric design, it has a better bistability by varying the arc lengths of the outer and inner shell segments. This allows the booms to be more reliable in both coiled and deployable states. The trade-off with this is that the improved bistability comes in reduced structural stiffness and is more complex to manufacture due to the different laminates that lead to thermoelastic deformation. The goal is to make a high structural boom that has a semi-asymmetric cross-section to have good stiffness and bistability.
The mechanized booms will pull out and unfold the solar sail from the main hub. This mechanized boom system has 4 booms that are extruded through 4 boom guides. The method of extrusion is a 2-spool system, and these 2 spools are attached to a geared frame connected to a singular motor.
The deployment mechanism is divided into 2 modules. Each extrudes 2 booms. The module consists of 4 separate sections: the plate, the spool, the lever arm, and the boom guides. The plate is the housing for all other parts and will be attached to the rest of the system. The spool contains the 2 compressed boom wraps and feeds them through the boom guides. The spool is made up of a cylinder with 2 sides shaved off. These flat sides are where the ends of the composite booms are adhered, further attached through compression by plates connected to the spool. The lever arms are meant to maintain compression on the composite wraps as they are extruded to keep uniformity and prevent blooming, which is when the composite wraps unfurl in a non-uniform manner. Not shown in the model, the lever arms will also have a spring on the rocker shaft to maintain compression. Finally, The boom guides are where the composite boom wrap is fed through. The guides buckle the booms into the ideal shape to support the solar sail.
With previous missions that highlight the maneuverability, like Light Sail 2 and Icarus missions, we are able to see extendability with ours as a cube satellite is able to take a propulsion sail system all the way to Mars. With solar sails, we're not just exploring space, we're showing that there's no limits to how far we can take a continuous, sustainable new form of propulsion. Historically limited to low Earth orbit, by creating a propulsion system to get us to Mars, who knows where our next destination will be.